In the last chapter, or the chapter before, in chapter 3, we learned about orbitals for the first time. And, there's much hand wringing and fear and everything else about, oh my God, quantum mechanics. And it's so desperately difficult. But I think, by the end of it, I think we sort of came out of the idea that it makes sense. We sort of like tied together the fact that shells and subshells and orbitals and electron spin and the way we looked at all that fit together perfectly with how the periodic table is put together. And you could actually read, if you took the periodic table and just went across, you could actually see how each atom introduced a new electron. We had an S block and a P block and a D block. And so you could see as you went across the table one by one, how each electron was being introduced and then taken into the atom, and how filled shells, when we had completely filled shells, that gave us very stable atoms. So the most stable atoms are the noble gases. And so we saw that helium has a completely filled first shell, and it's stable. And then neon had a completely filled second shell, and it was stable. And we just went down all the way down the line. Each time a new shell was filled, chemical stability was brought about. And we sort of explained how different atoms get together and share electrons, because by doing that, they were able to have electrons they shared together to fill each other's shells. And then that's how covalent bonding takes place. Well, I kind of have some bad news. It turns out that covalent bonding is a little more complicated than that. And so this is a relatively brief chapter, but I think it's important to sort of see, since we've learned about shells and subshells and orbitals and everything, and how different atoms share electrons. And then subsequent to that, in chapter 4, we learned about shape. We saw how the way atoms share electrons determine what shapes those molecules are. And so now we're going to put both those things together and see that the way that atoms share electrons determines the shape. And the shape also determines how they have to share electrons. So it goes both ways. So does anyone know what liquid is present here in this picture? Or wants to take a guess at what this particular liquid is?
Liquid nitrogen?
Could be liquid nitrogen. Could be liquid nitrogen. It's in fact liquid oxygen. And that's a magnet. So one of the things that we'll talk about at the very end of the chapter is this one of the problems with the theory we have for how atoms share electrons. That remember that when we had unpaired electrons all pointing in the same direction, that would become a magnetic atom. And we saw iron has a whole lot of unpaired electrons, and so it was magnetic. Certain other metals have very few, if any, unpaired electrons, and so they're not magnetic. But one of the things we thought we understood was that when two atoms came together and completely filled their outer shells, like oxygen, O2, or nitrogen, N2, or really any diatomic molecule, shares electrons that completely fill its outer shells. And if the outer shells are completely filled, by definition, they shouldn't be magnetic. The problem is liquid oxygen is magnetic. And so we can't explain that with the typical rules that we've been using for covalent bonds. And we'll learn about that now. Oh boy, oh boy. So I'm just going to take you through a couple of different theories of covalent bonding. There's a third one, and I'm going to talk about it next week very briefly. I'm not going to really hold you responsible for it. But it is the theory that explains how oxygen can be magnetic. And so I'll sort of take you through it, but I won't be testing you on it because it's fairly fairly intense, and I sort of want to keep going on to the gas laws. But the two things I will be discussing today are basic valence bonding theory, meaning that an orbital hybridization. What that means is that we have now a new kind of orbital, where we were discussing atomic orbitals before, S, P, D, and F sort of subshells, and how they are involved in atomic, the structure of electrons inside atoms. We're going to learn that when you have shared electrons, that those shapes that we learned about don't really fit for sharing electrons between two atoms. And a lot of it has to do with shapes that molecules have to do. And so we'll talk about the different kinds of overlap that these orbitals have, because we'll see that because orbitals are, by definition, where electrons are, that one atom and another atom coming together to share electrons, those orbitals that the electrons are in have to sort of intersect. They have to sort of overlap each other so that those electrons can be shared. And so we'll learn that when those shapes of these different orbitals have to be such that they can come in contact with each other. And so we'll learn that S and P and D and F don't do a good enough job explaining how they could possibly overlap and have covalent strong bonds through shared electrons that would allow that to take place. So a principle, a very basic principle of valence bond theory is that, like I said, orbitals have to overlap. And that makes a lot of sense because, since that's where the electrons are. So if I have an orbital, if you remember way back, you remember that p orbitals look like this. Remember, p orbitals could look like this. And then they went behind, and then they came out. So if I have a p orbital that's at these 90-degree angles to each other, and then I have another p orbital that comes close to it. If I have a p orbital up here and a p orbital down there, it's not really going to interact with this p orbital up here. They're not going to intersect with each other. And so if I need to share electrons between those two p orbitals, they're going to have to take on some sort of different shape in order for that to take place. And so the space formed by these overlapping orbitals will be able to accommodate the two shared electrons. And then they'll have opposite spins, just like we see in an atomic orbital. We'll have one pointing up, spinning up for plus 1/2, and we'll have the other spinning down for minus 1/2. So they'll have opposite spins. And the better the overlap between those bonds, the stronger that bond's going to be. So if I have two orbitals that completely overlap, so if I have, let's say, a p orbital in this direction, and here's the other atom, and it has a p orbital in the same direction, and they can completely overlap one another, that's going to be a strong bond. So basically, if I could share electrons directly between those two atoms, where they come into close contact with each other, those electrons that come into really close to each atom and completely overlap, that's going to be very, very strong. And so the amount of overlap depends on two things. What shape is that orbital? And we've learned that some of these orbitals have some very odd shapes. Mostly we're going to be sort of staying with S and P, but there are also, we talk a little bit about D as well. But the greater the overlap, if the shape is so that they come in, that they could cover each other, basically, that's a strong bond. And if they're sort of coming at each other in the same direction, or actually opposite directions, but if they come together pointing toward each other, that will also help maximize the overlap, and you'll get a stronger bond. So I'll sort of give you, right now it sort of sounds a little odd, but I will give you some examples to let you know what I'm talking about. For instance, let's look at the very simplest chemical bond we can think of. Two hydrogens coming together. So we know that in the hydrogen atom, it's only got one electron. That's it. And it's got it in the first shell because hydrogen is in period 1. So it only has room for 2 electrons. It has one S. And one hydrogen by itself has one S1. So here's the electron there. And the other hydrogen is in the same position, has one electron, also in one S1, both pointing up. Now, we know that the S subshell is a sphere, right? That's one of the things that we learned early on, was that the simplest way an electron can be held inside of an atom. The very simplest subshell is just a sphere. So the S orbital is basically like a circle that goes around the nucleus. And because of that, when Bohr looked at all the energy changes from that electron moving from one shell to another shell to another shell, he could calculate them very exactly because they're all shells, they're all circular, they're all spheres, they're all the same shape. And that's true for just hydrogen, as it turns out. So hydrogen and helium. So when the two hydrogens get together, these two shells are pushed basically till they overlap slightly. And then these two electrons come in contact with each other and basically form what we would call a molecular orbital. So we would have, instead of two singular, so here are two singular orbitals, 1s and 1s. When they overlap with each other, we would now have a molecular 1s orbital with one up and one down. And so that would be a covalent bond of sharing a pair of electrons, one up and one down. So that already, okay, that makes sense. S can overlap with S because they're both spheres. The atoms move close together, and we can see that they overlap. All right, fine. Now we have a second example. Now we have fluorine, and we know that fluorine's valence electrons, it's unpaired valence electron that it will be sharing with another atom is in the p orbital, right? Because fluorine has one space left. So if here is its 2p orbital, and it has 1, 2, 3, 4, 5. So it has space for another one right there. So basically, it has a p orbital that then extends towards another atom. And then when it overlaps with the orbital of another atom, this gets shared with, in this instance, hydrogen. So we have hydrogen and it's 1s, and so its spherical orbital overlaps nicely with a sort of, balloon-shaped orbital of p, and it shares that electron. Now we see it overlaps even better with another p electron because of the shape. The shape is more compatible. You see there's a lot of empty space, or a lot, not as much overlap with a sphere and that sort of long balloon shape with a sort of a longer shape. When they have two long sort of skinny shapes overlapping, they overlap better. And so this is actually a slightly stronger bond. The FF bond in fluorine is stronger than the HF bond in hydrogen fluoride because the overlap is greater. So the greater the extent of overlap without a lot of extraneous space, the better the bond. Now we'll start to see where the overlap makes even more sense. Oh, go to the next one. So the orbitals that form when bonding occurs are going to look different than the atomic orbitals we've been looking at so far. So because if no change occurred, we really couldn't account for the shapes that are observed. The angles and the shapes wouldn't make any sense. So I'll sort of explain what I mean. So atomic orbitals, what they do, they sort of mix together. So if, for that example of hydrogen fluoride, we had an s orbital mixing with a p orbital. So actually what we call that is a hybrid sp orbital, and that's how we're going to refer to them, as what two orbitals are being hybridized in order to make this sort of new shape. So an s and a p hybridizing together would be an sp. An s and two p's hybridizing together would be sp2, and an s and three p's hybridizing together would be sp3. And we'll show you what those orbitals look like and how they account for this, and how they account for the shapes. Let me clear. So some of the features of these hybrid molecular orbitals. The number of them, now remember, orbitals have room for 2 electrons, right? So each orbital has a little box that has room for 1, 2 electrons. So the number of these new ones that we form, so these new ones that we form will equal the same number of the number of atomic orbitals that we mix together, okay? But the type, the shape of these molecular orbitals is going to vary, and it varies with the kinds of orbitals that are mixed up. Like I said, if we mix an S and a P, we get an sp orbital that has a specific shape. S and two P's, we have sp2, that has a different shape. And sp3 has another different shape altogether. And so the shape and the orientation of these new hybridized, these new shapes of orbitals, what they do, in effect, is they maximize the overlap with the other atom. And you remember, the more overlap we can get, the stronger the bond is going to be. So basically what they're doing is forcing these orbitals to take the shape where we can get the maximum amount of overlap from one electron coming from one atom and one electron coming from another atom when they're shared. Because if they don't overlap strongly, you're not going to get a very strong bond. And so basically they will rearrange themselves into a pattern where the shapes and the bond angles that we became familiar with in the last chapter can be seen in these hybrid orbitals. So here's an example. So we have beryllium chloride. So beryllium has only 4 electrons. It has 2s, and there's s and p electrons in its available to it. So this is what an isolated beryllium atom would look like over here. Right, so it has, basically, it has a full shell in 2s. So its core electrons are 1s2, and then its valence electrons are 2s2. Well, if that's the case, when you think about it, if it has a paired, if these electrons are paired and they're stable, we'd have to break them apart in order to share them with another atom. And on top of that, if they're both in an s orbital, how are we going to be able to share them with two different atoms? So we've got beryllium, 2 chlorines. How are one chlorine on one side going to be able to share a 2s electron, and another chlorine on the other side be able to share the other one? That's not going to have very good overlap. So what happens is that we have what are called these hybrid orbitals. Now, since beryllium has its 2 electrons in the second, its 2 valence electrons in the second shell, there's also p orbitals available in the second shell. So what happens is it basically mixes those 2 orbitals together. It mixes the s orbital and it mixes the p orbital together and forms 2 hybrid orbitals. And so you remember, when you mix an s and a p together, you get an sp hybrid orbital. And this is what it looks like that. And you can see it sort of looks a little bit like the s orbital, and it also looks a little bit like a p orbital. But what it allows, instead of having a shape that looks like this having the 2s, the basic sphere, what it looks like now is it has this on one side and that on the other side. And this allows, so it has 1 electron here and 1 electron on the other side of the atom. And so it allows bonding on this side from an incoming chlorine and bonding on that side from an incoming chlorine. So this is sort of what the sp orbital would look like. Basically looks like it looks like a p orbital, but it's got a little more, the density you can see is a little different than the p over here. It's sort of stretched out a little bit more. And since it's stretched out a little bit more, it can overlap better with incoming electrons from other atoms. They'll give you show you an idea what that looks like when they overlap. So here's my S here on the bottom. So again, spherical shape, completely spherical. And I've got 2p, so this is my -1, my 0, and my +1 orbitals for p. And you remember they look like the sort of stretched out balloons and at 90-degree angles. And so instead of promoting both of these electrons up to 2p, it basically mixes with them. And so it has 1 orbital that looks like a p on one side and an s on the other. And this other one looks like a p on the other side of the atom and an s on the other. And so now this can overlap very effectively with an incoming electron on its left, and this could overlap very effectively with an incoming electron coming in on its right. So this is what the overlap would look like. So chlorine comes in. Oops, let me go back. Chlorine comes in, and just like the fluorine example mentioned a minute ago, the valence electrons for chlorine are in the p orbital, right? Valence electrons for chlorine are in the p. It has one unpaired electron in the p orbital. 1, 2, 3, 4, 5, and then it goes right there. And you can see that this p orbital from chlorine overlaps very nicely with this sp orbital from beryllium. Much better than the overlap of an S and a P did, like when we looked at hydrogen fluoride. That overlap wasn't as good as it was for the overlapping P orbitals. And so that bond isn't as strong. This overlap leads to a very strong bond because you can see that the shapes are similar. An sp orbital doesn't look exactly like a p orbital, but it's pretty close. And so you can see that this overlap is a lot better and leads to a stronger bond. So any questions so far? I realize that this is sort of some heady stuff, but basically all we're doing is we're mixing these two shapes together and coming up with a shape that overlaps better with other bonding electrons.
I have a question. When do you know
Sure.
overlap?
Oh, well, you know they overlap when they bond.
Oh, okay.
Yeah. So if the electrons don't overlap, they don't bond. And we'll go through some examples that will explain why certain electrons don't bond and certain electrons do.
Okay.
And yeah, hopefully, but sort of the first point I want to get across is that the way the atomic orbitals were set up work for atoms, because all of those electrons are local, right? All those electrons are local to that atom. And so those orbitals make sense. They work for how an atom is organized. But when you're organizing a molecule, it's a little more difficult. Then you have to take into consideration the orientation of all the different atoms in that molecule. And the way that certain atoms kept electrons to themselves is not going to work for when you want to share them, because then the shapes don't work out. And so what we've been able to come up with is by combining the different orbitals that we've learned about, we do then get the shapes we're looking for. And this is just the first example of taking an S and a P and mixing them together and sort of getting an idea of what those orbitals would look like and why it works better than just S by itself. So this is our first example, looking at beryllium chloride. Now we have boron. So we're looking at boron. And so we know that boron has 3 valence electrons, right? We know it makes 3 bonds. It is an exception to the octet rule because it's only got 3 electrons. And since electrons, a pair of shared electrons is a bond, it only got 3. So 3 is the maximum number of bonds it can make. One other thing I want to point out is what shape does, we sort of looked at some of these boron molecules when we talked about shape. What shape does beryllium trifluoride take on? Do you remember the shape that was? I know we're going all the way back to the last chapter.
Would it be planar? Like
Planar and, yep. Trigonal planar, right. It makes it, what's a fancy way of saying triangle. Yeah, it makes a triangle. So look at it this way. So if we have boron in the middle, and I have my one incoming fluorine there, and one incoming fluorine here, and one incoming fluorine at the bottom, 1, 2, 3 bonds. Now look, these, what's the bond angle between these 3, what's the fluorine, boron, fluorine bond angle? This angle right here. So it's a triangle. There's 3 bonds. So what are the angles of all 3?
120.
Yeah, exactly. 120 degrees. Now, how do we have 3 bonding electrons all with 120 degree angles to each other? Because here we don't have that. Here we have 2 electrons that are in a circular orbit, and we have 1 electron that's in a 90 degree angle. It's in a p orbital. Remember, p orbitals are at 90 degree angles to each other. So one, we have a circle, so we have, and the other we have a 90 degrees. That won't work when we make this particular structure. That can't happen. And the other thing that sort of throws a wrench in the whole works is that these 2 electrons, we remember there's an energy to these electrons, right? When we fill in, we do 1s, and then we do 2s, and then we do 2p, and then we do 3s, and the energies goes up the further and further we get away from the nucleus. So this 2s orbital is at a lower energy, and this electron by itself is at a higher energy. So we would expect that these 3 bonds would all have different energies, right? Because these 2 electrons are being shared are at a lower energy. This electron up here, hello, this electron in the 2p orbital is at a higher energy. So if we were to look at those 3 electrons being shared with other atoms, by definition, we would expect those bonds would have different energies because they have electrons with different energies. But that's not the case. Each bond is exactly the same as the other 2. So this electron and this electron and this electron all have exactly the same energy. They have exactly the same energy, and they're at 120 degrees to each other. And that just isn't possible when we look at the isolated boron atom. That is not the way the boron atom has its electrons organized. So something must have happened between when boron was an atom by itself and then when boron was in a compound with fluorine or hydrogen or whatever other atom it's in a compound with. The way it's organized its electrons in the compound is completely different than the way it organized its electrons in the atom. So what it has done here, it has taken its 2 electrons in the s orbital, and it's taken its electron in the p orbital, and what it's done is it's promoted these 2 electrons from s orbitals to a new hybrid orbital called sp2. And if you're wondering where we get these numbers from, it's because there's 3 electrons bonding, and we need 1 s orbital, and we need 2 p orbitals in order to hold them all. Because remember, they're going to be 3 separate orbitals because they're going to be bonding with another electron. And then that second electron is going to go in there, and in there, and in there. And so it will be a completely filled sp2 orbital. So the s and the p, it just tells you how many, well, s is always going to be 1 because there's only 1 s orbital. And the number of p orbitals will tell you how many shared electrons are we dealing with. Okay, and in this instance, we've got 3 being shared. So we need 1 s and we need 2 p orbitals in order to hold the 3 bonding electrons. The third 2p orbital remains unhybridized. Why? Because there's only 3 electrons. we'll see in a second, if there's 4, we're going to need this one. So you see how basically this comes right back to shape, because we were talking about, you remember when there was 2, when you had a central atom and there was 2 regions of electron density. We looked at that and said, well, that has to be linear, right? You have to have one area of density on one side, one area of density on the other side. So that makes it linear. That was an sp hybrid orbital. And then we saw when there was 3 regions of electron density, just like we have with BF3, the most stable conformation for that to be would be a triangle with 120, 120, 120, which is exactly what we have here. So that we need 2 more, we need an additional p orbital to get 3 bonding electrons. So that's sp3. And notice, when we have 2, it's 180. When we have 3, it's 120. Can anyone guess what the bond angles are going to be when we hybridize 1s and 3p for 4 regions? You remember what those bond angles were? When we had a pyramidal shape? Remember, there's sort of like 3 bond angles we had to remember. There's 180, 120, and what was the third one?
90 degrees?
Not 90, no. I mean, 90 comes later when we have like 5 or 6 regions. But when we have 4 regions, you remember we had with the
109?
109, exactly. Because that was the angle in a pyramid where we could keep the electrons as far away from each other as possible. And that'll be coming up. So this is what the boron looks like. And so you can see there's the 3 sp2s, and look at the shape of them. 120 degree angles. So we've mixed, so instead of 1s and 1p giving you this sort of shape on one side and that sort of shape on the other side, now we've mixed 3 of them together. And so now they're separated by 120 degrees. We get a similar shape. We still get that sort of bulbous, sort of stretched out shape that a p orbital has. But now that we have 3 of them, they're separated by 120 degrees. And you can see you get really good overlap between these sp2 orbitals because they're elongated and the sp orbital of an incoming fluorine. So these stretched out sp, sp2, and as we'll see in a minute, sp3 orbitals overlap nicely with incoming electrons. Now here we've got 4. And so this is carbon. So we're looking at carbon as the central atom this time. So carbon, we're well aware at this point, has 4 valence electrons, right? And so it's got, let me go back. And so it's got 2 in the 2s, and then the last 2 go in separate 2p orbitals, or -1, 0, +1 orbitals. Now, just like boron, this particular arrangement of electrons is not going to work if you want to make 4 bonds that all have equal energy that are separated by 109 degrees. This arrangement doesn't work. And it's not going to work. So one other way you could make it work, one could argue, is that you could just move one of those 2s electrons up here to 2p, and then we'd have 4 orbitals, all with 1 electron in them, ready to bond with another atom. Well, that could make sense, but then the shape wouldn't make sense because remember those p orbitals are at 90 degree angles from each other, in and out. Those are at 90 degree angles to each other. And then the third one is sort of in the middle. How is one atom going to interact with this, another one interact with this, another one with this one, and then the fourth one sort of got to wedge itself in somehow. So what we would see is three bonds that looked similar, and the fourth bond would be different. And we'd have 90-degree angles for three of them and a different angle for the fourth one. And they would be at different energies, like I mentioned before. This electron that would be left in the s orbital would be at a lower energy than the three that would be in the p. So we would think not only would the shape be different, where we'd have 90-degree angles, we have 90-degree bond angles because of the orientation of the p orbital, but we'd also have different bond strengths. But when we look at something like methane here, each one of those bond angles is exactly the same. Each one of those bond strengths is exactly the same. And so all those bonding electrons coming from carbon have to be exactly the same. And so having three unpaired in p orbitals and then the fourth one be unpaired in an s orbital doesn't work, because that's not what we see experimentally. And you may think with this is all sort of some craziness, but this is all backed up by experiments. If the electrons acted the way they do in atoms, we would see something different. But we don't see that. What we see is four exactly equivalent bonds with equivalent shapes and equivalent strengths. And that can only be possible if each one of those bonding electrons from carbon is exactly the same. And so the way that comes about is now we have four bonding electrons, and we have s, and we have p orbitals. So basically we're going to need all of them. We're going to need to hybridize all four together and put one electron in each one. So just like my other idea, like I mentioned before, you could move one of those electrons that's paired in the s orbital and move it up to p, but the energies and the orientation, the spatial orientation, does not work. So what happens is we have a different arrangement of those four electrons. And you can see the energies are slightly less. This hybridized orbital, this sp3 orbital, is slightly less in energy than p. Notice that it's down a little bit. When we do these drawings, remember when we do orbital diagrams, we draw them 1s, 2s, and then 2p. We draw them up as we go up in energy. Well, notice what's happened here. The hybridized orbital is slightly less in energy than the highest energy orbital where it hybridized from, but it's higher than the lower energy. So it's less than p, but it's more than s. And so basically, remember what I mentioned, s electrons that are lower energy than p electrons, and we should know that by now. Basically, if you averaged all the energy of these and these, would be exactly the same as this, because the energy remains constant. We don't lose any energy forming these. We don't gain any energy forming these. They have to be the same. So that's why the energy of these hybridized orbitals is slightly less than the highest, but more than the lowest. Sort of, it's a mix. It mixes everything. It mixes the orbitals, it mixes the shape, and it mixes the energy so that they're all equivalent. And so when you have four orbitals all completely equivalent to each other, and remember, electrons arrange themselves into a shape where they least come in contact with each other because they're negatively charged. That's why we figured out it's linear when there's two, and it's triangular when it's three, and it's tetrahedral when you have four groups. That's as far away from each other as these 4 unpaired electrons can get from each other. And by doing that, they allow themselves to bond with hydrogen here, there, and there. So there's maximum distance between all of them. Any questions about how we're mixing these orbitals together, and how we're like referring to them as sp, sp2, sp3? Or is everyone's just sort of dead inside at this point?
Not dead inside, just processing.
Okay. Processing's better than dead inside. Okay, good. And remember, this is going to be the test tomorrow, so relax, everybody chill. But I think it does an excellent job. I like going over things that explain what you see in nature, because then it sort of gives you a better idea of like, well, why the hell is this? Well, it's because of this. Why are these bond angles? Oh dear. Did we lose you? Did we lose everybody? Are you still there?
Still here.
Oh, there we are. Yeah, it dropped out for a second. Good. Whew. Okay. Now, let's look at ammonia. So, in this instance, nitrogen has 5. Oh, my dear, what are we going to do with 5? The thing is, nitrogen only makes 3 bonds, right? And so you would think that it would be fine. We've got these 3 unpaired orbitals in P, and again, we got our old friends. Whoop, let me go back. We have our old friends -1, 0, and +1. And we're looking at that, and it's like, yeah, fine, perfect. It's got 3 unpaired electrons, makes 3 bonds, fine. It's got a lone pair, yeah, there they are, right there. Problem is that, remember, that doesn't fit with the shape of the molecule. Thus, since p orbitals have that 90-degree angles to each other, if we shared those 3 electrons the way where they are in the atom by itself, we would expect the bond angles to be 90 degrees. But it isn't, because it takes on a trigonal pyramidal shape. It's in the pyramidal family, right? And so it doesn't fit with this particular organization of electrons. So what happens? Well, it's got 5 electrons, and it needs 3 places for bonding. It also needs a 4th place because it has a lone pair. Well, let's do that. Let's hybridize the 1s and the 3p, so we have sp3. And the numbers tell you how many orbitals are involved. So if it's sp3, it's got to be 4, right? 1s and 3p. It tells you that there's 4 places for electrons to go. So here's our 4 places for electrons to go and 5 electrons to put there, because, as we all know by now, nitrogen has 5 valence electrons. So let's start putting them in. So we go 1, 2, 3, 4, and then the 5th one goes there. And the 5th one now, that particular orbital is now full. That is your lone pair. And then these other 3 unpaired electrons in the sp3 hybrid orbitals, they go on to form bonds with hydrogen or whatever atom they're in. This explains why ammonia has the shape it does, because that lone pair of electrons basically is in the same shape, it's in the same orientation as the bonding electrons. And so it can't be in a different place. They can't be in an s orbital and all the bonding electrons are in p. That doesn't work. It's in the same orientation as the bonds are. So it has to be in the same sort of electronic arrangement that the bonding atoms are. And an sp3 hybridization does this. It allows all four of them to be at 109 degrees. And then when we have the lone pair, and here's our lone pair up here, what happens to the bond angles when we have a lone pair on top here? Are they going to be pushed down to less than 109 degrees, or are they going to be a little higher to above 109 degrees? What happens when we have a lone pair? So we've got a bond here, and a bond here, and a bond there. So are those bond angles going to be more than 109 or less than 109? So basically, they're going to be pushed, or they're going to be stretched out. Oh, somebody take a guess.
They're going to be pushed?
Exactly. Yeah, because remember, we learned in the last chapter that lone pairs basically don't have any atoms around to diminish that repelling force of those electrons. And so a lone pair does a really good job of repelling the other electron groups. And the other electron groups in this instance are bonding groups. And so these angles are going to be less than 109. So it starts at 109. When it's the nitrogen by itself has those shapes, but then this lone pair is going to push those other electrons further away from it because it's twice the density of electrons. So it's going to push it so that those angles are slightly less than 109. And then when we look, so we would predict that the arrangement of electrons around nitrogen would have bond angles of less than 109 degrees because one of those orbitals is twice as full of electrons as the other three, and that's exactly what we see. So it describes it extremely well. Now again, we have sp3 hybridization, this time with water. Now we have 6 electrons hybridizing. So what's going to happen this time? Because before, when we looked at it, the first time we came across the way that oxygen organizes its electrons, we saw again that it's got these. Oh, let me go back. Damn you. It's got these 2 electrons. So we figure, okay, that's a lone pair. And it's got these 2 electrons together. Okay, that's a lone pair. And then these 2 p electrons would then be available for bonding. Made perfect sense. However, we remember that if that were the case, we would have either a linear molecule, or these 2p orbitals would be at some sort of 90 degrees from each other. And we don't see either one of those. It's not linear, and it's not at 90 degrees either. It has an angle of around 106. So where does that come from? Well, it comes from the fact that we need to hybridize all 6 of these electrons. And when we do that, we take our 1s and our 3p, because remember, what period is oxygen in? Do you remember? It's in the 6th group, but what period is it in?
2.
2. There you go. Someone had their notebook open to their periodic table. Great work. Yes, it's in period 2. And because it's in period 2, it only has s and p orbitals. That's it. It doesn't have anywhere else to stash electrons. It doesn't have any fancy places like D where it can like move extra, where it can move extra electrons around. It obeys the octet rule. So we need basic space for the octet. We need to make space for that octet. And an octet has 8. And so space for an octet would be 4. And so we hybridize all the s and p orbitals together so that we have 4 of equal energy. We have 4 of equal energy, and we have 4 of equal orientation. And so then we start filling in our electrons. And we fill in electrons to a hybridized orbital exactly the same way we do with normal atomic orbitals. So we would go 1, 2, 3, 4, 5, 6. So this one is filled, this one is filled, and we have 2 unpaired electrons available for bonding. And this is what it looks like down here. So you can see that those 2 lone pairs of oxygen are equivalent. They're equivalent to each other. They're in the same orientation. And that is impossible if we don't hybridize the orbitals, because then one of those lone pairs would be an S and the other lone pair would be in a P. They are not equivalent. But that's not what we see in nature. When we look at the water molecule, we see that both of those lone pairs are equivalent to each other. They're in the same orientation. And then they're in the same orientation as the bonding electrons are as well. And so the only way you can do that is with 4 equivalent bonding hybridized orbitals that fit 6 electrons. And so when you fill them in, 2 get completely filled and 2 are empty, or 2 are not empty, 2 are unpaired. And that's where the bonding orbitals come from. And so we get the bent shape because we have an electron group there, electron group there, there, and there. So it's in the tetrahedral family, but since it's only got 3 atoms, it looks like it's bent. But it's not bent to 90 degrees as we would expect it if it was in a p orbital, and it's not linear. No, it's bent the way we would expect a tetrahedral arrangement of electrons to be. Okay? Let me clear that out. All right. Now it starts to get weird. I sort of threatened it was going to a little while ago. But remember, we have 5 and 6. We have atoms that make 5 and 6 bonds. What are we going to do about that? Well, remember, what kind of atoms can form 5 and 6 bonds and violate the octet rule? What's unique about those? There's something different about those atoms and the ones that can't violate the octet rule. What do the atoms that can violate the octet rule, what do they have in common?
They have d orbitals.
Yeah, they do. Yeah, they're in period 3 or higher. They have d orbitals. And so since they make 5 or even 6 bonds, if they make 5 bonds, then they need 5 orbitals. And so I take my S and my 3p. Well, that's only 4. Hey, I've got d orbitals I can use too. And so the same thing happens. We take our p, and we take our s, we take our 3p, and we steal one of those d orbitals. So now we have a total of 5. And then we hybridize those so that they all have the same energy and the same orientation to each other. And so then I have my 5 orbitals, and then I start filling them up. 1, 2, 3, 4, 5. So I go 1, 2, 3, 4, 5. Oh, I have 5 places to put incoming electrons from other atoms of all equivalents. And so that's what I get. And so we just call that sp3d. And that tells you how many were used. 1 from S, 3 from P, 1 from D. 1, 3, and 1, that's 5. 5 places where electrons can gather. And so, and you see now the energy, note that this is what the energetic it's what the electron organization looks like when we draw it out. We've got the P at the bottom. We got the S at the, I keep calling that P, I don't know why. So we have 3S at the bottom, and then we go up a little higher, and we have 3P, then we go up a little higher, and we have 3D. So 3D is the highest energy. Well, look, now that we've added a D orbital, look and see how the hybridized sp3d is almost the same energy as P, because I've added additional high energy orbital from D. So it's pushed the average energy up even higher. So whereas sp3 was here, was a little bit lower energy, now that I've added a D, it's gone up a little bit. And so it's pretty much the same energy as a p orbital. But now I have places to put 5 electrons. Any questions so far? See, we just keep adding orbitals. We just add as many orbitals as we need. When we need 2, we're going to take an S and 1 P. When we need 3, we need 2 Ps. When we need 4, we need all 3 Ps. And now that we need 5, we've run out of P orbitals. There isn't any more. So we go up further to a D. Now, what do you think happens when we need 6? What are we going to do then? Let some lucky customer guess how many we need. 5. So with 5, you need an S, 3 Ps, and 1 D. But if we need 6, what are we going to do? Oh, someone's got the guts to answer.
Will it change the orbital?
We'll need another orbital. Where's it going to come from? So now we'll need 6 orbitals. So we'll have 1s and 3p. Where are my other 2 going to come from?
From D?
Yeah, so what do you think we're going to call it?
D2?
Bingo. Yeah, we're going to call it sp3d2. All right. Excellent. See, I don't yell at you that much. There we go. So sulfur is a classic example of an element that makes 6 bonds. And so when it does, when it needs to have 6 bonding electrons, it now needs 6 electron orbitals to put them in, right? And so you can't just, in this arrangement, we look at it and we remember that sulfur and oxygen are in the same group, right? They're both in group 6. And so when we look at sulfur, it has 1, 2 unpaired electrons in its p orbitals. So we would think, well, just like oxygen, it should only form 2 bonds. And a lot of the times it does, like when it forms dihydrogen sulfide, which is that stinky, stinky gas. A lot of the times it does form just 2 bonds, and that's fine. But a lot of the times it forms 6, and we can't explain that like this. And so what it does, and as it turns out, we also need the hybrid orbitals to explain this as well, because the bond angles of H2S look just like water. And so it uses sp3 hybridization for this, because it has 2 bonding electrons and it has 2 pairs, 2 lone pairs. So it has 4 regions of electron density, so it needs sp3. But oxygen can't make 6 bonds. It's physically impossible for it to do, because it can't violate the octet rule. Sulfur can, because sulfur has access to d orbitals, because it's in the 3rd period. It has added another shell. It now has d orbitals available to it. so what happens is then now we need 6 orbitals, 6, of equal energy. And so it takes the 1s, so one of the s's, 3 of the p's, and 2 of the d's, and hybridizes all 6 so that it has equal, each one of these has equal energy orbitals to the other one. And so 1, 2, 3, 4, 5, 6, they get filled in one at a time. And now notice the relative energy of the sp3d2 orbital is now higher than 3p, because now we've added 2 d orbitals to it and increased the energy even more. So now the energy is even a little bit higher than the p, but all of these would be equivalent to each other, which they have to be, because when it forms 6 bonds, in this instance it's forming 6 bonds with fluorine, every one of those 6 bonds is the same energy and they're all in the same orientation. They all have that octahedral shape. So all of these are 90-degree angles from each other, all identical. So sort of just a sort of basic take-home lesson of sort of fills in everything here. Hopefully this will sort of make a little bit more sense when you sort of just step back and think about it a little bit. But when I want 2 regions that are equal, what I need to do is mix 1s and 1p. When I want 3 regions that are equal, I take the same 1s, but now I need 2 more p's. When I need 4, I need to add another p. But when I need 5, I've run out of s and p orbitals. I don't have any more. I need to add 1 more d. And then when I need 6 places to bond, I use my same s, the 3 and p's, and now I need 2 more d orbitals in order to fill them all. And that's where we get the names from. sp, sp2, sp3, sp3d, sp3d2. And so all you need to do is just add the numbers up and see how many equivalent electrons are there. S and P, that's 2. sp2, that's 3. And so when you're thinking about how many bonds is it making that are all equivalent to each other? Now, one important thing I should mention, because we're getting to it in a minute, these are all single bonds. Have you noticed that? These are all single bonds. So it's a single shared pair of electrons. So each of these hybrid orbitals had 1 electron in the hybrid orbital, so it would share with another 1 electron from an incoming atom that would overlap. Now, when we're talking about double bonds, it'll be a little different, and we'll get to that. Any questions on this is the single bond world of hybrid orbitals. Hopefully it makes a little more sense now than it did half an hour ago. We'll have time to go over it a little bit later. We'll go over it again next week when I introduce the really weird stuff.
Would we do the recitation for this?
Yeah, we'll have a recitation on this. Yeah, definitely. Yes, this is how so far we've learned about how to make a formula, right? We learned how to balance formula, how many atoms are going to be involved, where the electrons go. So we make a Lewis structure out of that to see how they're going to arrange themselves. And then based on the Lewis structure, figured out what shape that's going to be. And then basically, then we sort of go backwards to figure out, based on that shape and the number of bonds, that tells us what hybrid orbitals are involved with making that shape. So if it's tetrahedral and it's making, we have 4 regions of electron density, that tells us we have sp3. If we have, because we look at the shape, it has 5 regions of electron density, and we're thinking in the back, 5, that's S, 3's only got, it must have a D in it. And then that's how we work out the orbitals. So basically, we sort of start with atomic orbitals to figure out what the Lewis structure is. But then when we put them together in a molecule, and we've learned about how those molecules are shaped, then we basically sort of work backwards a little bit and figure out what the molecular orbitals must look like. All right. So I'm going to look just to take you through a couple of these. And so we're going to look at methanol and sulfur tetrafluoride. So let's have a look and see how we use the atomic orbitals of the central atom, and then we convert them to hybrid. We basically use the Lewis structure to figure out the arrangements of the electrons. So here's what methanol looks like. So basically we have a carbon here. It sort of basically looks like methane. So it's got a tetrahedral arrangement around that carbon. And it's a tetrahedral arrangement around the oxygen as well, because we know that oxygen basically, when it bonds, it has 2 bonds and 2 lone pairs. That's also tetrahedral. Therefore, they're both going to be sp3 hybridized because they're both tetrahedral in shape. And so remember how we did that for carbon. Carbon had 4. And so we had 4 half-filled sp3 orbitals and made 4 bonds that looked identical. And oxygen has the same basic shape, the same tetrahedral shape. It's a little more bent because of the lone pairs, but it's in the same family of tetrahedral shapes. So it also needs 4 regions. So it also has sp3 hybridization. There's our 2 lone pairs, and there's the 2 bonding electrons there. So yeah, then when we look at sulfur tetrafluoride, remember sulfur has 6 valence electrons. And so since it has 6 valence electrons, and it's sharing 1 electron each to the 4 fluorines, it's going to have a lone pair left over. Therefore, it has 5 regions of electron density, right? It has 5 regions of density. Well, if it has 5 regions of density, it needs 5 places to put electrons. And so we know that it's sp3d hybridized. That's the only way to get 5 orbitals of equal energy. So the isolated sulfur atom, we know, looks just like oxygen, right? There's our isolated sulfur atom with its 2 in S and 2 in P, or sorry, 4 in P. Since we need 5 places to put electrons, you use 1, 2, 3, 4, 5, S, 3 Ps, and a D. And then we fill in the number of valence electrons. Sulfur has 6 valence electrons. So we go 1, 2, 3, 4, 5, and then come back and put in the 6th one. There's our lone pair right there. And then those are the 4 electrons that make bonds with the fluorines, okay? So there's limitations to this model. There are some problems with it, which shouldn't be a shock to you. There are limitations to the atomic model. Oh my God, you mean there's limitations to the hybrid model too? Yeah. So it's particularly true for when you're bonding with like larger atoms. For instance, I mentioned before that H2S kind of looks like water because it has sulfur with 6 electrons, just like oxygen has 6 electrons. It's bonding to hydrogens, just like water's doing. But the bond angles are a lot closer to what we would think unhybridized orbitals would be. So remember I said p orbitals have 90 degrees to each other, right? P, this way, this way. Those are 90-degree angles. That's really close to a 90-degree angle and a lot different than what we see with water. So it's like, something's weird there. And also, d orbitals don't really hybridize effectively with s and p because d orbitals are really high in energy. And so we don't really see the hybridization working as well with d orbitals, but we sort of force them to because that appears to make sense. So just before we go, let's wrap this up and then we'll sort of review it again on Monday. I've only been talking about sigma bonds. Sigma bonds are bonds formed by these end-to-end overlap of orbitals. All single bonds are sigma bonds. So sigma is the kind of bond where I have 2 orbitals. There's one here and then one there. They overlap with each other, and then I have my electrons in the middle, sort of forming an orbital. So it's basically, a sigma bond is formed directly between 2 atoms, and they share those electrons with orbitals that are directly in between them. So any time 2 bonds make a single bond, that's the way they make it, with these sorts of directly overlapping orbitals. That's why they go through all that trouble of the hybridization to make these weird shaped orbitals so that they'll overlap. But you also have double bonds and triple bonds. Those are formed when you have sideways overlap of orbitals. And I'll show you what those mean. And those are called pi bonds. You may have heard of sigma and pi bonds when you're back in high school. So sigma, all single bonds. All subsequent bonds to that are called pi bonds. So a double bond would consist of one sigma bond where that electron is shared directly, that pair of electrons is directly in between the 2 atoms, and a pi bond, which would have these sort of sideways overlap of orbitals. Why is it sideways? Because they're always p orbitals. That's why they're called pi bonds, because they're made with p orbitals. That's how I remember. And so if I had a triple bond, that first bond would be sigma, and then the second 2 would both be pi. So anytime the first bond that's made is always sigma, because it's directly overlapping. But then if another one forms, that's pi, and if a second one forms after that as well, it's also pi. Now I'll show you what those look like. So here we have a structure where all single bonds. So we have a single, let me go back. Okay. Here we have all single bonds. So this carbon has 4 bonds, this carbon has 4 bonds. Nobody has more than one. Everybody's sp3 hybridized. Everybody's 109 degrees. Everything's normal. But and so there's even distribution of electrons all the way around because they're all the same angles, they're all the same orientations, pretty even distribution of electrons. And they're all sigma, remember. Now, let's look at that basic same structure. If we remove 2 of those, hydrogens and replace them with a double bond between the carbons. So this is the way that works. I'll sort of just wind up here and let you get to studying. So this is the way this works. So we have sp2 hybridization now between the carbons, not sp3. Why? Because there's now 1, 2, 3 regions of electron density around each carbon, not 4 anymore. Now it's only 3. And so it forms sp2 hybridization because it needs 3 sigma bonds, one with this hydrogen, one with that hydrogen, and one with the adjacent carbon. And so you can see those sp2 orbitals here. These are the sp2 orbitals in the middle. Now remember, sigma bonds directly overlap. But where does this other bond come from? Well, the other bond comes from the p orbitals, which have not been hybridized. So you remember the p orbitals, there's p orbitals left over that have not been hybridized. And so since carbon has 4 valence electrons, it's only put 3 of them into hybridized orbitals. sp2, that's only 3 electrons. It's got an additional 1 left over, and that's in a p orbital. And since the p orbitals are at 90 degrees to each other, we've got electron density above the 2 carbons. We have electron density below the 2 carbons. And that's where we get a double bond. So the electron density is not, with the sigma bond, the electron density is directly in between the 2 carbons. With a pi bond, it's both above it and below it, because that's where the p electron is, okay? So I'm gonna wind up there, and we'll sort of review a little bit of this on Monday, and I'll sort of just take you quickly through why liquid oxygen is magnetic, because it's kind of cool. But I'm going to leave you with this. Any questions about hybridization? I imagine your brains are probably melting at this point. You just want to study. I understand. Anybody have any questions about it? Everybody's in shock. Okay, I will just wish you good luck tomorrow.
Professor, just I have
Yes.
a quick question.
Yes.
I answer for any calculation question. I should look to the significant
Digits, yes. Significant
in the
digits are
last
important.
step, in the end, in the final answer, or should from step
Final
by
answer
step?
only. Final answer only. When you're doing your calculations, carry over as many digits as you want. Like if you're calculating grams to moles,
Mhm.
and you have a molar mass that has like 7 significant digits in it, use them. Use them all. But when you get to your final answer, it should represent the proper number of significant figures. So if the question only has like 4 significant digits in it, you can't report all 7.
Okay.
But use them. I always use as many as I can find all the way through, because you have a more precise answer that way.
Okay.
Yeah, that's a common error that students make. They round things way too early. Because you've seen, like, if you looked at the problems we worked on this afternoon, some of them were 3, 4, 5, 6 steps. So you carry those digits all the way through till you get to the very end, and you'll get more accurate answers.
And for the digit, let's say if like 278.3,
Mm-hmm.
these contain 4-digit number.
That's
Oh,
4.
okay.
Those are 4 significant digits. Yes. Yeah. Any non-zero number is significant. Anything else before we wrap it up? All right. Good luck, everybody.
Thank you.
All right.
Thank you, Professor.
so,
Have a good
have-
weekend.
You too, and have a good review with Dr. Gagrab tonight. Ask him lots of embarrassing questions that he doesn't know.